All right, so let's look at an example of boiling water. So in this problem, I ask, how much heat is required to completely boil 500 milliliters of water at 22 degrees Celsius? And as I point out, when I say completely boil, I mean nothing left in the pot. Every last drop of water has been turned to vapor. So how much heat is required to completely boil 500 milliliters of water at 22 degrees Celsius, which is about room temperature? We're boiling water that starts at room temperature. So this is actually going to use up both of our new equations. We're going to use Q equals mc delta T. This is the equation for changing temperature. So Q equals mc delta T, well, that's how we change the temperature, because before this water boils, it's got to get to 100 degrees. First, we need to raise the temperature from 22 degrees Celsius to 100 degrees Celsius. That's the first thing we're going to do. And then after that, we're going to use Q equals mL. And is it going to be V or F? Well, in this case, it's going to be mLV because we're crossing that liquid-gas boundary. It's the latent heat of vaporization because we are vaporizing the water. And this equation is used to change the phase from liquid to gas. So it's going to be a two-step problem. First, we change the temperature. Second, we change the phase. And so let's look at that. First, let's use Q equals mc delta T. How much energy does it take to heat the water up to 100 degrees? Well, we know we have 500 milliliters of water, and that's the same as 500 grams of water. Remember, milliliters are the same as grams when it comes to water. The specific heat of water is something we can always look up, but water is one that is actually particularly easy because it is just 1 calorie per gram degree Celsius. And then our delta T, well, to compute delta T, we need to know our final temperature. It's going to end at 100 degrees, and we need to know our initial temperature. It begins at 22 degrees Celsius. All right, well, that should be all the information we need. Q is computed by mc delta T. We know M, we know C, and we now have the pieces to compute delta T. So Q equals M 500 grams times C 1 calorie per gram degree Celsius times delta T, which is T final, 100 degrees Celsius, minus T initial, 22 degrees Celsius. Well, altogether, that little piece is really 78 degrees Celsius. And if we multiply all these things together, we see grams canceling with grams. We see degrees Celsius canceling with degrees Celsius. And we get 500 times 1 times 78. We get 39,000 calories. And we can convert that to joules by multiplying by 4.186. 163,800 joules of energy. Now that's just the energy to raise the temperature to 100 degrees. The second step is to use Q equals mLV to change the phase from liquid to gas. So Q equals mLV. Well, we know we have 500 grams of water, and we can look up the latent heat of vaporization. That is 540 calories per gram. So plugging those numbers in, Q is going to be 500 grams. How much of the substance we have that is going to be changed to a different phase, and how much energy is required to change every gram of that substance to a new phase. So 500 grams times 540 calories per gram. We see the grams canceling, and we are left with 270,000 calories which would be 1,134,000 joules had we used, if we just wanted to convert this to joules, or had we used the latent heat with the units of joules instead. But are we done? No, we're actually not done yet. We want to know the total amount of heat. So the total heat is actually how much heat it was required to raise the temperature to 100 degrees, added to how much heat was required to then boil all of that water. So 39,000 calories plus 270,000 calories. The grand total is 309,000 calories. And of course, we could convert that to joules if we wanted by multiplying by 4.186 joules per calorie. All right, but that is a nice basic example involving both of our equations from this chapter. First, how we change temperatures. Second, how we change phases. And if we want the total amount of heat required for that entire process, we need to add all of our steps together. All right, so we'll stop there for this video and come back talking about conservation of energy in terms of heat.